Well, hello everyone. Welcome back to our course. Let me go ahead and open up in prayer and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, Lord, thank you very much for the chance to be working with each of the students in this course. I pray that the material will be clear, that it can be interesting and fun, and I pray that it's going to be instrumental for everyone as they navigate working towards getting the degree of their choice to get the job that they would like or opening a business of their own choosing. Pray, Lord, that you would help them in their spiritual formation, Lord, that every student can see the value and really cherish in their heart the times that they can be studying scripture to get to better understanding of its messages and understand the theological concepts in which we can be applying it to the various things, various situations that we face in our life. Give them interesting and creative ways for faith integration. In Jesus' name we pray. Amen. Okay, I'm going to continue the process of what I tried to introduce on Tuesday. This second section gets fairly technical, and it is, as an engineer, as compared to a physicist or a mathematician, these are all the resources that you use trying to find technological means to be helping you to accomplish a goal. And there's another textbook that I will be introducing some material like I did on Tuesday to help make this a little bit more accessible and point out with that engineering or computer science mindset as a way of thinking about it. So we're clicking through each one of these concepts. We talked about the things that we measure, the length related variables, how we measured length and volume. We talked about time. Time is real critical and cross-cutting both between engineering and computer science, mass-related efforts, and force. And so for this lecture, we're going to be thinking about temperature and temperature-related variables. And so I will keep this at a high level like I did on Tuesday, and then have us think a little bit more from our project sense and the things that we have from this other resource that I'm getting a chance to leverage. So maybe I'm sure that you guys are familiar with temperature, and I don't know how many of you have visited other parts of the world, whether it be Europe or other places where it's more common for there to be using Celsius versus Fahrenheit. Anybody have had that experience either on vacation or some other means? You can just do a thumbs up if that's something that you're familiar with. Okay, at least some of you have some awareness that it's um, people do look at it differently in different parts of the world. And that's what the thing I'll focus on here. And then there's a couple of concepts that gets into this chapter, and temperature is a fundamental dimension. And so by getting familiar with this material, we'll be able to describe the role of temperature in engineering and computing, analysis, and design in its units and measurements. So Celsius, Fahrenheit, Kelvin, those are the ones that will be most common for us. The temperature difference in heat transfer, explain what causes heat transfer, the mode of heat transfer, and what is meant by thermal resistance in the R value. Maybe some of you have been aware that you put insulation in the walls or in the up in the attic to try and make a home more maintain its temperature the way you would like. And so R value is one of the ways it expresses how well it's good at preventing thermal transfer. Thermal comfort describes the factors that define thermal comforts. And so there's a temperature range that we feel comfortable at. Those that have pets, it can be a little bit different. They might want it a little bit warmer than what we might feel comfortable with. The heating value of fuels explains what the heating value of fuels represent. And then there's degree days and thermal energy estimation explains what is meant by degree days, describes how engineers estimate monthly or annual energy consumptions to heat buildings. And finally, additional temperature related material properties, and that can help us to explain what is meant by a coefficient of thermal expansion and specific heat. So some of the things, once again, get a little bit complicated, and I will just give a very brief introduction of that. But temperature is something that's quite common, and regardless of engineering or computing discipline, you'll need to develop a good understanding of what is meant by temperature and how it is quantified. Civil engineers need to have a good understanding of temperature when they design pavement, bridges, and other structures. I remember this one time when I was on a business trip in Phoenix, Arizona. Anybody been to Phoenix, Arizona during the summer? Guys have an idea that it gets pretty warm out there? Well, anyway, as I was walking across the asphalt from where I parked my car into the entrance to the building, I could turn around and I could actually see my footprints in the asphalt. Just to go to show you, it was so hot, it was actually melting the asphalt. That could be an example. Well, and if you're in Phoenix, Arizona, you might have to design things slightly differently. Mechanical engineers design heating, ventilation, and air conditioning, or what's commonly called HVAC equipment, to create a comfortable environment. So keep it within that comfort range of what we would like to see. So there's various ways that we can be measuring temperature. We can be using a thermocouple. That's one thing. There's these thermal resistor and RTD. And so these are just examples of some of the things in different scenarios. One might be better than other. Thermometers is maybe what you and I are most familiar with. And so it based on the temperature, the fluid is going to expand. And so using alcohol or mercury are common substances that are used for that. We have various conversions. We've already talked about that. And so here it gives an interesting way for us to be thinking of why would we be using these two temperatures to have on our scale, one being 0 here for ice water and one being 100 for boiling water. So I'll just put it over here and we can have a little bit of a dialogue, anybody that wants to go off mute. So in the Celsius scale, under standard atmospheric conditions, the value 0 was arbitrarily set to the 0 at which water freezes. So a very common substance, use that as a calibration point, and 100 is when water boils. So this is how they can actually calibrate a new thermometer to make sure what those temperatures are, and then you can go between those, and it's a linear scale. Anybody have an idea what this temperature would be in Fahrenheit? You can put it in the chat if you'd like. 32, right. And maybe some of you might recognize what that would be for boiling point of water in Fahrenheit. And even if you don't, these are the kind of numbers that you can look up in table, and it's not something that you have to memorize. But if you use something a lot, it tends to be something that you easily can go to. So thank you, Christian, for contributing there. So temperature differences and heat transfer. And so this is how you can go from one region to another. Heat always flows in a high temperature region to a low temperature region. And there's various units, BTU, calorie, or joule. Some of you may be more familiar with calorie in terms of like having a 2,000 a day caloric intake. So BTU is maybe something that you may have heard. Maybe if you or your family was having to buy a new air conditioner or heating system, those are the kind of numbers, the type of units that you would be seeing. So conduction refers to that mode of heat transfer that occurs when a temperature difference exists in a medium. The energy is transported within the medium from the region with more energetic molecules to the region with less energetic molecules. So if it's warmer outside, and you go through some type of medium, the heat transfer is going to be where the cool area is, and it's going to warm that up. And the degree in which it does is going to be reflected to the um, heat conducting properties of this material. So that's a little bit of perspective there. We mentioned the R value. The R value of material provides a measure of its resistance to heat flow. The higher the value, the more resistance to heat the material offers. So it's going to minimize this transfer of heat using this example of a window. I don't know if some of you have double pane or triple pane windows, maybe in your home or your parents' home, or you've been aware of that. That's one of the things that it can help to reducing that heat transfers. You have multiple panes of glass, and you either have air or some other noble gas that's put between those panes that's trying to reduce that transfer of heat. This might be a familiar picture. Anybody ever looked inside maybe if you have a desktop computer, this would be something that the configuration that we're seeing here. Anybody know what this is? What is this thing down here? Anybody want to take a guess? Yeah, it's a central processing unit, Zay correct, and Bach. That's also it's an air cooling system. I remember I had a Volkswagen, and it's an older style Volkswagen, and it had an air cooled engine. So it was like this, but a lot larger. And so when you have these fins like this, it creates more surface area for that the heat to escape, and the fan helps to get the air to brush through those fins more often and force that heat away from the CPU. And so this just gives you an idea of how we're using convection. I have a little Raspberry Pi, and it doesn't generate that much heat. So literally it just has a heat sink, and it doesn't have a fan, and it still keeps it at a nominal temperature, which works just fine. But for a CPU that you're using it for lots of computation, it's going to require something like that. This could be an example of both on the engineering and the computing side where you're going to bump into this. You need to make sure that your environment for a software engineer or computer scientist, they have to make sure that their hardware is still functional. And this could be one of the things that you could be statusing is what is the overall temperature of your motherboard. And for those that are in engineering, this would be something that you're trying to make sure that everything is according to spec. So you're going to be working probably more on the hardware side, and the computer science folks are going to be more thinking that, well, how is this going to impact the functionality of my software? So radiation is another term for electromagnetic radiation, if you've ever heard that term. All matter emits thermal radiation as long as the body in question is at a non-zero absolute temperature. The higher the temperature of the surface of the object, the more thermal energy is emitted by the object. And so there's a term called black body radiation. And so when we're thinking in some areas of measurement, it's not a big deal, but in other places it is, like the James Webb Space Telescope. Anybody familiar with the GWST? I know I've mentioned it before. Anybody seen some of the images that come from the James Webb Space Telescope? And it's operating at a frequency in such, it's called the infrared, where the black body radiation of what you're generating makes a difference. And so they're trying to keep that temperature of the telescope as close as possible to absolute zero. And that 0 degrees Kelvin as they can on the side that's facing where they're doing their measurement. I'm not going to get into too much detail. So thermal comfort, I think we're all familiar with this, but not everybody has the same kind of ability to regulate temperature. So humans have the ability to sweat. Some of you that may have a dog, they don't sweat, but actually through their tongue, you ever seen a dog with its tongue sticking out and it's dripping water off its tongue? That's one of the ways that they cool themselves, as well as having faster breathing. So you can be thinking a little bit like this example of what we were trying to show with this the CPU and the conduction of heat that we're trying to show there. That's what a dog is trying to do. Blood circulation near the surface of the skin. When you get hot, the blood tends to go to the surface of the skin. The metabolic rate. Some of you that work out, it actually is raising your metabolic rate and it makes you feel warmer. And so you would actually could feel comfortable in a cooler place until your body starts to recover from working out. So the basic metabolic rate is one factor controlling a person's body temperature. And we more or less 98.6 is the temperature that the body likes to keep itself at. There can be a little bit of a range for normal. Having it a little bit below that is not a big deal. But if it gets above that and significantly above that, that's when you're running a fever and something that you want to be concerned about. So what makes us thermally comfortable in environment? I think you guys have an idea here. Anybody ever thought about how humidity would impact us? What happens when it's a high humid day? Anybody have experience? Maybe some of you are from the South or the Southeast. Maybe you've experienced high humidity. If you get into 90 or 100% humidity, you think that's going to make it more pleasant or less pleasant? Anybody have a thought about that? Yeah, good one, Zaid. I agreed. It's interesting here on the West Coast, when you go in the water's cooler, but I've had a chance to go swimming in the ocean in Florida, and it's like going into a sauna. And then you get out of the water and the humidity is like 80, 90, 100%. And I remember going running in Louisiana one time when it was warm and humid, and it just like somebody had put leg weights on my arms, on my legs, and then on my hands, and it just was really hard to get much of anything going. So here's some other things that we'll talk about. The heating value of fuels. You can be thinking about that. I'm just going to skip over that for now. Degree days and heat estimation. This sounds kind of complicated, but if I show you a figure, and I will in a minute, if we start to give some kind of an average of annual or what is the temperature per day, this is an example of a heat map of looking at the annual trends for what the temperature would be. And I'm not going to try and explain the scale. It just gives some way that you could figure out. And so I mentioned Florida tends to be pretty hot there. Southern California, it's warm, but it's a little bit milder, at least for on average, as compared to say what it would be in Florida. And it's roughly that the lower latitudes are hotter. The further north you go, it gets cooler and cooler. And so those are just some thoughts here that you can see that gives us a little bit of a sense of these degree days and energy estimation. How much is it going to cost to maintain that temperature where we're comfortable at on different parts of the country? That's just one way to be thinking about that. Thermal expansion. it's interesting, like your car is sitting in the sun, and if all the material is the same type of material, it's probably going to be fine as they expand. Um, but like you could have like the gap between your front door and your back door and stuff like that. That would be an example where you could see that it starts to grow or shrink a little bit depending on the temperature. And so this is going to be one of the criteria that engineers are going to have to be thinking about when they're just figuring out how they're going to lay out things. And so I saw this one picture, I don't have it here, but a physics course where they showed railroad tracks, and they didn't allow for the railroad tracks to expand, and they actually warped when it got really hot. And so instead of going in a line, they were just going in an S fashion because it was trying to relieve all of that length increase when it got warm, and vice versa. It's going to shrink when it gets hot. So those are just some things out there, that there are some more specific things for us to be thinking about in this lecture. Okay, just a quick little run through of thinking about another value here. These are the fundamental types of things that we got a chance to be thinking about in chapter 6. And we get a chance to be reviewing that. We have a couple more that we'll be looking over. But does anyone have any questions here? So a couple more comments. Like Zaid, heat equals tired. Yeah, for sure. And I know for me, I tend to work out and feel like I have more energy if it's a cool day than if it's a warm day. And I'm going out and trying to get a workout. So let's move over to this other textbook, and I'll get a chance to be introducing this a little bit more here. I took a section from this textbook for our discussion on Tuesday, and I wanted to give a little bit of a broader introduction to today. And so this is a textbook that I've used for an introduction to engineering course a couple of times. But this was a course where it's both engineers and computer science, and I wanted to try something a little bit different. But the 3 sections that it has here, it calls lead on. So this is like an introduction to what engineering and computing is about. Then minds on is when we're actually figuring out, well, what exactly are we going to be focusing on? And this gets into some of the differences between the different related fields that fall into this area. And then the last section is a hands-on. It gets into the details of going through this process of making it happen. So the lead on, what engineers do, we got a chance to be talking about that. We talked about elements of engineering analysis. This is where I had that 4-word summary that we were using to give us another way of thinking about how we go about doing it. Talking about force and motion, energy. These are the things that we've got a chance to be introduced. We talk about the economic side of engineering. All those are true. Then in the middle part of this book, it gets into all of these different types of engineering, and computer engineering is the one that's a little bit of a crossover. There's software engineering, there's computer engineering, there's computer science, there's communication, computer information systems. All of those are there. And there's some emerging fields that are starting to come up. But I also want to be focusing on this hands-on section of trying to figure out how we do engineering design. And so we have these various steps: defining the problem, generating alternative concepts, evaluating those concepts, doing detailed design, having a chance to have peer review, and then you get into the manufacturing and testing, see how well it performs, and then you have a final report for what we're doing. So we're not going to be doing any manufacturing, we're not going to be doing any testing, but we're mostly going to be focusing on these beginning ideas of defining the problem, coming up with maybe one or more alternatives. We've had some of those type of discussions in our dialogue here. Some of you have come up with an idea and some of you have been morphing it a little bit. That's perfectly fine. A good practice is not just to let those other things go, but make sure you annotate it so someone else comes look at what you did, they can say, ah, now I see how they got from point A to point B. They were looking at various concepts, various options, and found that some things work and some things don't work. So any comments or questions on what I've talked about so far? Okay, well, I'm going to just spend a few more minutes doing a look at this beginning of this hands-on. So this let's do this introduction to engineering design and both engineering and computer science. So what is the nature of engineering design? It's not a single valued answers. And so you can be thinking about some of the development that we were looking at, ways that we could turn plastics into oil. We've had a couple other things, and I'll circle back to our list of projects in a few minutes. And so the importance of teaming is also quite helpful. And so in the future, you're going to have a variety of different expertise coming together, and as a whole, they can articulate what the big picture is with a combination of all of those things, and it's going to help have a better design, and it's going to help each one of us become better designers. There's a couple ground rules for successful designing. There's a need for a systematic approach as well. And we may or may not talk about an exercise here, but we'll see how far we get in what we're doing today. So what's unique about design? Unlike homework problems, there are no unique answers. That's one of the things that's nice about the project work. It's no right or wrong. It's you are doing the methodology to come up with a solution and showing your work and seeing what it produces. You can make an airplane that would be 100% in an accident, but it would be too heavy to fly. You can see there's these competing criteria that sometimes come together that you have to be thinking about. So how do you achieve a design balance among competing criteria? So as a result, most designs are hands-on, meaning you have to build and test a working prototype. So let me go to our project list and take some of this information and see if we can start to play this out a little bit more. So we have all semester to have two places where we're going to be reporting out on our design. First thing is the halfway point of the midterm review, and then our final. And so we've had several people that have mentioned that they wanted to have us focus on their project first, and we have. So we talked about turning plastics into oil. We had a little bit of discussion about the solar mobile phone charger. We'll come back to that, but we also had a discussion about magnetic slip-free shoes and other things. And so what do you think would be some of the competing criteria? Let's just choose one of these. How about the magnetic slip-free shoes? What do you think some of the criteria, competing criteria would be to make this work? Anybody want to throw out an idea or two about that? Either go off mute or put it on chat. Okay. Andrew was asking for me to repeat the question, and so let me try and help out and give you a concept about this here to make sure I set up the question and then repeat the answer better. So this is what I'm trying to get. How do you achieve a design balance among competing criteria? So anybody have an idea what they think the competing criteria would be for magnetic slip-free shoes? What would be one of the criteria that would be important to consider? You can reflect on our conversation that we had on Tuesday some. Okay, so Andrew mentioned accessibility and effectiveness. Each one of those things there's actually two of those comments, and each one is noteworthy for us to be thinking about. Budget and cost. And once again, those are both things that are helpful to point out. So accessibility, the way that we had set this up, we were trying to help people that maybe have mobility challenges to keep them from falling down. And so if we had magnetic sensors in the shoes, that would be the first thing of what you're trying to do is trying to sense that. So we're trying to deal with an accessibility audience. And and then in terms of effectiveness, okay, we do that sensing, then what's the next step? What can we do to prevent them from falling? Then what another person was saying was, well, what about budget and cost? And what I would suggest is those are actually two things. And so a budget is typically when you get funded, let's say that you're trying to go in front of a venture capitalist or go on Shark Tank and you're trying to get them to fund what you're working on. They're going to say, well, tell me what the budget, what is the budget is, that you foresee that it's going to take to make this a viable product. That would be one thing. And then cost, well, how much is it going to cost for these magnetic slip-free shoes? What is your unit cost? And so there are some related things that are stuff that we would need to be thinking about. Does that make sense? You guys following along as we're thinking about what it's like to think like an engineer or computer science and to be setting up a problem and solving it? Okay, good. So most designs are hands-on, meaning you have to build and test a working prototype. And so how are we going to make a working prototype? That's a good question. So let's see if you have you're looking for a working prototype. What would be the type of magnets that we would be using? Are these commercially available? Or do they need to be manufactured because there's nothing in a form, fit, and function that you need? What kind of shoes are you going to attach these magnetic sensors to? What other kind of controls are going to be in those shoes? You can start to see how some of those things start to come up and could be an issue. Teams are needed because the magnitude of most projects is too large for one person to handle. I would also argue that not everyone has the subject matter experts to do everything. So this gets into this teaming and characteristics and trying to get the overall capability of a larger set of people to help you to figure this out. Let me see if I can get some feedback either on the magnetic slip-free shoes or any other of these concepts that you think would be some of the concerns that would be coming up for making them a success.
You're like asking what kind of questions could come up with the success of like our project, so to say.
Yeah, yeah. I'm just trying to walk through this section of an introduction to engineering design. And now we're trying to think about um, the first thing that come up is, well, how are we going to start to make it real for engineers having a prototype? For software folks, it could be having a minimal viable product of a functioning bit of code that you could start to say, does this actually meet what we envisioned that it would be? Does that help, Andrew?
Yeah, thank you.
Okay, feel free to share your comments if anything comes up after clarifying it a little bit more there.
Well, I guess for my project, the extracting oils from plastic, I guess some things to consider is I think I mentioned in the last class, like what kind of plastics would be used
Mhm,
and what kind of I guess what kind of oil would be extracted, because I mean taking it oil just like that would probably, break the machine.
mhm,
Like how do I say it? Take extracting the oil just like that without like doing anything to the oil itself would probably not work on as fuel for like anything. So I
mhm,
guess the question that I'm trying to consider is once we've extracted that oil, what's the next step?
mhm. Yeah, and let me pull up the article that we had. Where would I put that? So, well, let's focus on Andrew's project for a little bit, and then we'll come back to one or more of the other ones based on who would like to share a little bit. And so I'm just going to be focused on this graphic down on the bottom here. You can see here is our sample of plastics. Let's just say this is all plastic. It's not quite the same, but it does give you a sense that there's a lot of different types of materials, different types of plastics, plastic bags, plastic bottles, tires. And so you just put this all into a blender, and now you're going to be processing that. What are you going to get? And so this is where it gets into you need to start to be planning things out. Um, so according to what this environment energy company is using is they heat it to a certain temperature range and then add a catalyst to break, um, uh, which then converts them into the hydrocarbon gases. These are then concentrated into crude oil. So you're returning it to crude oil. And what you have to do is, like, if you've ever been around an oil refinery, they take in crude oil, and then from that crude oil, they turn it into various types of petroleum products, which it gets into what Andrew is mentioning. And so, how are we going to design an overall system to be showing all that? And so, a good way to be conceptualizing it is having a block diagram of what are these steps. So maybe step one is collecting the materials, doing some type of sorting. Like, for example, they have like some various materials that isn't plastic, paper, wood, metal, separate those. So then you have a, a subset of that. Maybe it's like you just, instead of just having all of the garbage, you try and get the blue bin garbage that is recyclables to make this a little bit easier for you to work on that. Then you heat it to a certain temperature. Then you add the catalyst at a certain rate as this is being processed, creating the crude oil, and then you have to become up with doing it with that refinement of that crude oil to what type of oil products that you would like. So let me turn it back over to you, Andrew, to see if you have any more thoughts or comments on that.
Thank you.
Okay. Anybody else have a project that they'd like to have us talk about in this context? Including one of the ones we haven't talked about in detail yet. Well, I'll just arbitrarily just scan through and Saul, you want to tell us a little bit more about your project, and let's see if we can start to unpack it a little bit in the context of what we're covering today.
Yeah, I believe I already talked as in depth as I could about it a couple of weeks ago.
Yeah, tell me which one is yours, just to give me
It was the number 2 automatic solar tracker.
okay. So yeah, so I think maybe you have a good understanding of how to proceed. Like, so I presume you're an engineer as compared to a computer science, is that correct?
Yes, I'm a mechanical engineer.
Mechanical. So like what I was just mentioning for Andrew, having a block diagram of what were the steps to be doing this tracker, some type of visual to show that flow would probably be a helpful thing for you to be including as we start to lay this out. Maybe you've already got that conceived in your mind. Maybe you even have that on your interim development that you've done on your project. But any comments on that?
I haven't like made a physical diagram or anything. It's just been in my mind,
Mhm.
and it's been almost, I would say, stuck there in my mind. But I'm sure I'll find a way to proceed and transfer that to the physical world so other people could see it very soon.
Yeah, I find for technical communication, figures are important. This is different than if you're writing a short story or a poem or something else that's more in the humanities side. Um, the amount of information and technical information that you're trying to convey lends itself that having figures and graphics can really help out a lot. So, but anyway, thank you for sharing a little bit more, Saul. And but I'll continue to maybe think about what you're doing and everybody else as I just press forward a little bit at a time here. So a good designer is curious about how things work. Okay, that's an intriguing thing. And so I'll try and give both an engineering perspective on that as well as a software perspective. And so um, so a light motion detector system, I don't know exactly what that is, and maybe the whoever is doing that project can give some insight into that. But I'll just give you a motion detector system example. Like we have a garage and we have some motion detector sensors, and when someone is walking by, that's what it's meant for. It turns the light on and hopefully it scares away the bad guys. And if it's the good guys, they have illumination so they don't trip and they're able to get a little from point A to point B. So that's gives us a little bit of a sense of what we're trying to be thinking about with that project. So how does it work? You know, when you're just looking at it in operation, you're not really getting the details of what's going behind the scenes. And so is it have like a radar? Does it, everybody know what, when I say the term radar, does that something you've heard of? You can just use the thumbs up button if you've heard of it. And if I don't get too many thumbs up, I know that that's a concept that's not too familiar to you. So a few folks know about it, like Elon Musk, with his electric vehicles that are aiming towards being autonomous. They have various technologies, and one of them is using radar to see how far things are away from you. A lot of cars now have these kind of sensors where maybe if you're in a fairly modern car, you'll hear beeping because like the frequency that another car is transmitting is matching the frequency what you expect to have it receive and respond that, oh, okay, they're near to me. Or you're backing up in a parking lot and you get too close and it is informing you that's something that needs to be considered. So that would be an example of what could be available in a motion detector system, but how well does it perform? What is the technology? How large of an object does it have to be before it detects? How far away can it detect whether something is moving? We live at the end of a cul-de-sac and we go up to the top, the street that's there, there's a house on the other side of the street. And when I'm walking on the sidewalk and it's across the street, it's so sensitive that it turns on the light when I'm like 50 feet away. And so it's just a fairly sensitive type of thing that's there. Well, what about for software? I really, the thing that I like about open source software is you can actually see how individuals are doing their coding. Some of the coding classes that I teach, getting a chance to see the authors share their coding style, you get a chance to say, oh, wow, that encapsulation that they did really makes that really clean and neat and reusable and extensible. And so those are some things that you can be thinking about. Python is really great, and we'll be talking about Python later in the course, where they have all these libraries that you can leverage, and they've already done all the hard work, and they just have this API that you need to call to have that in your code, and voila, you can do fancy graphics, you can do various machine learning type of implementation options, and the list goes on and on and on. So does that help a little bit for thinking about having curiosity? A good designer is curious about how things works and trying to observe that. Does that make sense? You guys tracking with that? Okay, getting a few reactions, that's good. A good designer can manage several simultaneous tasks. This might be something useful to think of with you being in school. What happens when you get stuck in one class? Why not just put that on pause and go to another class and work on that? And then you can come back to that one that you put aside with a fresh set of eyes after you've been focusing on something else. And so multitasking can actually be a useful thing for a designer for a lot of different reasons. You work on this alternate task for a while. And, you know, by the way, some of the methodology here would apply to this first one. Why don't I get a chance to be leveraging them? That can be helpful. A good designer engages all the team members. Some of you are in your senior year and you're doing your capstone projects, and this may be the first time you're being forced to work as a team. But you're going to be getting a much better design when you do that. You're leveraging the expertise, the feedback, the peer review that you're getting from all of those folks and not just yourself. And then another thing that happens is a good design pushes a team without seeming to. And so you get into it, you get passionate about it. And everybody just really, they like it and they really want to make sure that it's the best that they can do. So that's just another thing that starts to happen with every project as things start to go forward. Ground rules. And so the first one is to use a design notebook. And so what the thing is that they're trying to say is you want to record what you're thinking and what you're producing. And so having a book, so it's bound together. So everything that you're creating, you're going to be able to refer back to. And so sometimes it's called a lab notebook. And this can be a really important bit of information that it's your first response in an informal way of what you're producing to lay it out. Anybody ever had to have a lab notebook? Maybe for some of your classes, if you've taken a physics course, this may be something that you've had to do. Anybody have used a lab notebook before? Okay, some of you are familiar with that. So it's something that you would have these things, page numbers, margins, lined. You can have some that it's actually graph paper. And so lines that are parallel, vertical and horizontal. So it's going to facilitate for you making graphs. I mentioned those block diagrams. This is a way that you could be doing it that way and just getting some of those conceptual ideas fleshed out. Then another thing is when you're working in a team, you need to have a team leader. You may be able to have it successfully work where you're just doing things in consensus. But the team leader may be the person that is pinging everybody, reminding people of deadlines, doing the things that everybody agreed to and says, we all agreed to do this, and now our deadline is this next Thursday, something like that. So a team leader may be assigned or spontaneously arise from the team. So you'll see that some people just naturally have those leadership abilities and you want to leverage that. The team leader is a participant, not a supervisor, and leads by example. That's another thing, is he's doing the work just like everybody else. Successful teams assign clear roles and work assignments. The team leader fosters good internal communication in the team and shares leadership responsibility, and team decisions are done by consensus. Does that make sense? Well, it doesn't apply since we're doing these on our own, but you want to be being your own team leader, managing your time and what you're going to be doing. So here is the systematic approach: defining the problem, generating alternate concepts, evaluating and selecting a concept, detailing the design, doing a design defense, manufacturing and test, and evaluating performance, and finally preparing the final design report. So the rest of this part of this book goes into those in detail. And so that might be a good place to break in terms of going through this material in this alternate text that I'm talking about. Yeah, so then they just have an example that they go over. So we're going to be doing something like this. We're going to be defining the problem, generating one, hopefully more concepts, having some way of doing an evaluation of those, and then having some degree of a detailed design where it's still a paper design, so meaning that it's a high-level design. And then with our final reports, we'll have some level of defense of that, or sharing it among the team. And so that's what we're going to be covering with our projects. Okay, any other comments or questions that people have, or anything else that you'd like to cover as we're finishing up our time together? Is this conversation helping you all? Is this, we walked through some of the designs that we've talked about already and some new ones. We're going to continue to try and broaden that as we go along. Okay, well, I think we'll have, that's a good breaking point. And I hope you all have a wonderful rest of your day, and I'll look forward to seeing you all next Tuesday. God bless now.